Hello and welcome to tutorial 13. Our topic today is an introduction to acids and bases, pH, and buffers. Before we get started, just a quick reminder that the notes to accompany this tutorial video are available online through my website. And with that said, let's go ahead and get started by talking about some characteristics of acids and bases first. So let's write up here on the board, characteristics and we'll make a column for acids and another column for bases and draw a line down the middle. Acids have a sour taste. Let's write that up there. Sour taste. And they're fairly common to find in the foods that we eat. So for example, citrus fruit, vinegar, which contains about a 5% solution of acetic acid, soda are all examples of foods that contain acids. Bases have a bitter taste. So although they're not very commonly found in the foods that we eat, they are very commonly found in our cleaning supplies, such as Windex and drain cleaner. Now, because we're starting out by talking about the taste of acids and bases, I do want to just quickly remind you that it is never safe to taste a chemical in the chemistry lab. Certain organic dyes will change color in the presence of an acid or a base. And so we utilize these dyes in the lab to quickly and easily check to see if a solution is acidic or basic. And one of the more common dyes that you might have already seen in the lab is litmus. An acid will turn litmus paper red. So I'm going to write here, turns litmus paper red, while a base will turn litmus paper blue. Now, the Arrhenius definition of an acid tells us that an acid is a substance that will produce hydronium ions in an aqueous solution. I'm going to write that definition down here. So acids produce hydronium ions. Hopefully you recognize that as H3O+, and that's in an aqueous, all right, AQ for aqueous, solution, all right, SOLN for solution. The Arrhenius definition of a base tells us that a base is a substance that will produce hydroxide anions in an aqueous solution. So I'm going to write that down here. Bases produce hydroxide, remember that's OH- in an aqueous solution. Okay, and this is the Arrhenius definition. I'm going to write that down in blue right over here. This is the Arrhenius definition for an acid and a base. So what does that definition really mean? Let's show what it means through a chemical reaction. So I'm going to go ahead and draw a Lewis structure for a water molecule, because this is in an aqueous solution. And for my acid, I'm going to pick HCl. And again, I'm going to draw a Lewis structure here because I want to do something a little different. I want to show the direction of the electron flow in this chemical reaction. So a reaction mechanism. I'm going to show the direction of the electron flow with curved arrows, and I'm going to use the blue pen to do that. So we've got this lone pair electron on the oxygen of our water molecule. The lone pair of electrons is going to be attracted to that acidic hydrogen of the acid. And it's going to lend, the water molecule is going to lend that lone pair of electrons to formation of a new bond with that acidic hydrogen. That acidic hydrogen is going to leave the 2 electrons in this covalent bond to the chlorine atom, going to leave that behind, both of those electrons behind, on the chlorine. And so once the water picks up that acidic hydrogen, it becomes H3O with a 1+ charge. So we now have that covalent bond to that hydrogen there. There's another lone pair that didn't react. Okay. Now notice that the hydrogen left both of these electrons behind on the chlorine atom, creating a chloride anion. So hydrogen left with no electrons of its own. It left its electron behind. That means that all the hydrogen has then, because hydrogen atoms just have 1 electron to begin with, all that hydrogen has left is its proton, or with a 1+ charge. And that explains why our hydronium ion has a 1+ charge, because the hydrogen came as just a proton. There's no electron to balance out the 1+ charge. The chlorine now has 2, 4, 6, 8 electrons all to itself, and therefore a 1- charge. All right, let's talk about how bases produce hydroxide in an aqueous solution. There are actually 2 ways that this can occur. So I'm going to write 1, and then I'll put a 2 down here for the second method. The first way is through the dissolving of a metal hydroxide base. So sodium hydroxide, for example, will dissolve in water to release sodium cations and hydroxide anions. And we looked at the dissolving process in quite a good amount of detail in tutorial number 12. So we already have seen how cations and anions of ionic compounds dissolve into the polar solvent water. The cations and the anions dissociate or separate from one another and become completely solvated by the water molecules. So this dissolving process, remember, this is just a physical change. This is not a chemical reaction. The second way that a base can produce hydroxide anions in solution is through a chemical reaction. So let's use ammonia, NH3, as our example. And again, I'm going to draw out the full Lewis structures and show the electron flow in this chemical reaction with water to produce, this time, hydroxide anions. Okay, so we have a lone pair of electrons on that nitrogen. Those lone pair electrons are going to be lent to the formation of a new bond with that acidic hydrogen, leaving behind the electrons in this bond on the oxygen, resulting in the formation of an ammonium cation, because once again, remember that the hydrogen leaves its electron behind, bringing with it only a proton, so only a positive charge. So overall, we'll have a 1+ charge on that ammonium ion. And then what's left over here? This hydrogen was removed. The electrons remain behind on OH, or the hydroxide anion. So it gained an electron, so it has a 1- charge. Okay. Now electrolytes are substances that can produce cations and anions in solution and are therefore capable of conducting electricity. Well, notice what we have here with our acids and our bases. We have the formation of ions in solution. So acids and bases are both classified as electrolytes. I'm going to write that right here, electrolytes. Now, most of the acids and bases that you will deal with in the lab are in aqueous solution. And so the Arrhenius definition is a very important one for you to understand. However, acid-base reactions do not have to be in aqueous solution. They can take place outside of an aqueous solution. And so the Bronsted-Lowry definition of an acid and a base can be much more useful and broad. So let's talk about that next. The Bronsted-Lowry definition of an acid tells us that an acid is an H plus donor. I'm going to write that here, H plus donor. And a base is an H plus acceptor. I'm going to write that over here. And I'm also going to label that the Bronsted-Lowry definition over here. And so let's take a look at a reaction occurring outside of aqueous solution. Let's just look at what happens when ammonia, NH3, reacts with HCl. And this reaction is taking place in the gaseous phase. So let's go back to our blue pen and indicate the electron flow here. You're going to have this lone pair of electrons picking up the acidic hydrogen. The electrons here are left behind on the chlorine atom to create a chloride anion. And the products are ammonium cations, 1+ charge, because this hydrogen brings with it a proton only, with a 1+ charge, no electron to balance out that 1+ charge. And a chloride anion, because remember it now has 2, 4, 6, plus these two, 8 electrons all to itself. It has gained an electron. All right, so in this reaction, let's label in blue, NH3 is our H plus acceptor. It is accepting an H plus and turning into the ammonium cation. So that is the definition of the Bronsted-Lowry base. HCl is losing the H plus. It is the H plus donor. And that is the definition of a Bronsted-Lowry acid. I'm going to write acid here. Okay. So let's just go back up to these ionization reactions that we wrote up here for the acid and the base and take a look at them just a little bit closer. And I'm going to use the green pen because I know it's getting awfully busy up here on the board. Okay, so in this reaction, clearly the HCl is donating the H plus. It's the H plus donor. I'm going to write here, H plus donor. Therefore, it is the Bronsted-Lowry acid. Notice though that water is accepting the H plus. Water is behaving as the H plus acceptor, making it the Bronsted-Lowry base. Now let's go over here to this other ionization equation for ammonia. Ammonia is accepting NH plus from the water molecule. So ammonia is the H plus acceptor, making it the Bronsted-Lowry base. Water is donating the H plus. It is the H plus donor in this reaction, making it the Bronsted-Lowry acid. An H plus donor is an acid. So what's going on here? Is water an acid? Is water a base? Well, really, we don't think of water as being acidic or basic. However, water is what we call an amphiprotic substance. And an amphiprotic substance is capable of donating an H plus or accepting an H plus. So, accepting an H plus here, donating the H plus here, depending on its surroundings. In the presence of a stronger acid, it's going to be the H plus acceptor. In the presence of a stronger base, water is going to behave as the H plus donor. So let me write that. Let's see if I have just a little bit of room down here. Let me just write the definition of an amphiprotic substance. Amphiprotic. Right, a substance capable of donating an H plus or accepting an H plus, depending on its surroundings. Okay, we don't have any more room on this board, so let's go ahead and erase here and go on to talk about strong versus weak acids. Okay, let's talk about strong acids first. A strong acid is an acid that will give up its H plus easily, and it will therefore be 100% ionized in an aqueous solution. I'm going to write that up here. Will be 100% ionized in an aqueous solution. I'm going to abbreviate that. Okay, so for example, let's take a look at hydrochloric acid, HCl plus H2O. We just saw a moment ago when we talked about characteristics of acids that this is going to ionize to hydronium and chloride anions. Because this is a strong acid, we expect this to be 100%. And so if we have a solution that's labeled 0.1 molar HCl, then we know that in that aqueous solution there is, of course, water because it's aqueous, but there's also hydronium cations and chloride anions. There will be no covalently bound HCl because HCl is a strong acid and will 100% be ionized in an aqueous solution. So I'm going to write here, no HCl, no covalently bound HCl. It has all reacted. So there are 6 strong acids, and you should probably memorize all of them, because if you just know the 6 strong acids, then by default you know all the weak acids as well, because anything that's not on that list is considered a weak acid. So I'm going to go ahead and write down the 6 strong acids here. HCl is one of them, HBr, HI, HNO3, HClO4, that's one that we maybe haven't seen before, that's perchloric acid. And let's see, 1, 2, 3, 4, 5, what did I miss? H2SO4, sulfuric acid. So hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Those are your 6 strong acids, and they are written down for you on slide 3. All right, so what then is a weak acid? I'm just going to erase these 6 strong acids, because I want this definition for a strong acid still up here on the board. And we're going to talk about weak acids. Okay, so a weak acid would be an acid that does not give up its H+ as easily, and therefore is not 100% ionized in an aqueous solution. So I'm going to write here is less than 100% ionized in an aqueous solution. Okay. So let's just use acetic acid as our example of a weak acid. That is HC2H3O2. Now you might remember when we talked first about how to name different acids, we said that in an introductory chemistry class you're typically going to see acids written with the acidic hydrogen first. So even though acetic acid has 1 and 3, 4 hydrogens total, only one of them is acidic, and that has to do with the way that the atoms are covalently bound together. Okay, so only one acidic hydrogen here. Now we're going to show that reacting with water. And it is an acid, so it will still give up some H+ to H2O to produce hydronium. Okay, so H3O+, which leaves the anion here, C2H3O2 with a 1- charge, the acetate anion. However, I'm going to write an arrow back, because we don't just get all forward reaction here. I'm going to label this with an F for forward. We're also going to have significant reverse reaction. I'm going to label the reverse reaction with an R. Okay. So this reaction is going to reach an equilibrium where we don't just have all products in solution, but we have some covalently bound acetic acid, HC2H3O2, is floating around in there. Of course, water, because the water is our solvents. We have a lot of that. That's just assumed. I'm not going to write that down. We do have some hydronium. It is an acid after all. And we do have some acetate. Okay. So if this is a 0.1 molar solution of acetic acid, we would have all of those things present in that solution, not just product. This reaction will reach an equilibrium where both reactants and products, both the forward and the reverse reaction, are occurring. Okay, so I'm going to write here an arrow, and I'm going to say we do have HC2H3O2. We do have that covalently bound acetic acid in that solution. Okay, so I did write these concentrations for a reason. Let's take a look at the concentration of the hydronium ion in the strong acid, the hydrochloric acid solution. Since we get 100% ionization here, the 0.1 moles of HCl that you would find in 1 liter of that solution will be completely converted into hydronium. And so the concentration of your hydronium in this solution, I'm going to write H3O+ in brackets. When you write that in brackets like that, that means you're talking about the concentration of that substance. It's going to be equal to 0.1 molar. You're going to have 0.1 moles of hydronium per liter of that solution, because the entire 0.1 moles per liter of HCl reacted to give you 0.1 moles per liter hydronium. In the weak acid solution, you will have a hydronium ion concentration that is far lower. I'll just write less than, but I'll indicate far less than the 0.1 molar concentration. Because if you have 0.1 moles of acetic acid per liter of solution and not all of it is reacting, let's say a very small percent of it is reacting to produce hydronium, then you're not going to get all 0.1 moles per liter converted into hydronium. You're going to get less than that. Okay, so you're going to have much less hydronium ions in that weak acid solution. All right, so some interesting things going on with this weak acid. Let's take a look here. We said we have a forward and a reverse reaction, and that we have an equilibrium reached where we have both reactants and products present in our solution of that weak acid. So let's look at our forward reaction, and I think it's pretty clear to say that the acetic acid is the H plus donor, and therefore this is our acid, and that H2O is accepting that H plus in the forward reaction to produce hydronium, and so this is our H plus acceptor, and so water, that amphiprotic substance in this case, is behaving as the base, the Bronsted-Lowry base. Well, what's happening in our reverse reaction? A reverse reaction is also taking place in this solution. What's happening in that reverse reaction? Well, H3O plus is giving a proton back to the acetate and regenerating acetic acid and H2O. So H3O plus is actually the H plus donor in the reverse reaction. In fact, let me write that in green just to keep them separate. Okay, so this is our H plus donor, which makes this our acid in the reverse reaction. So I'll put this in green and I'll put the F in blue to kind of keep that straight. Okay. And the acetate anion is accepting a proton in the reverse reaction, and therefore it is the H plus acceptor, which is a definition of the Bronsted-Lowry base. Okay. And the equilibrium is always going to favor the side of the reaction with the weaker acid and the weaker base. And so this reaction is going to favor the reverse direction because H3O plus is a stronger acid than the acetic acid. Okay, so we're really going to have a lot less hydronium ion than you might at first glance think. Now, there's something interesting about the acid in the forward reaction and its relationship to the base in the reverse reaction. Notice that their formulas are off by just one hydrogen ion, just one H plus. We call the acid and the base that are off by just one H plus from one another a conjugate acid-base pair. Let's label that in the black. I want that to stand out from all the color here. This is a conjugate acid-base pair. Same thing for the H2O and the hydronium anion. They too are related as a conjugate acid-base pair. Okay. And conjugate acid-base pairs are going to be fundamental to you understanding buffers when we get to our final slide today, which is slide 6. Okay, so just a little foreshadowing there, recognizing a conjugate acid-base pair as two substances that are just different by the presence or absence of an H+. Okay, let's go ahead and erase here. Okay, let's talk about strong bases next. And strong bases will have a high affinity for an H+. And the most common strong bases are going to be your metal hydroxides from group 1A and group 2A in the periodic table. So I'm going to write up here, have a high affinity for an H+. And the most common strong bases are your metal hydroxides from group 1A and 2A. Okay, so for example, sodium hydroxide, potassium hydroxide, calcium hydroxide, these are all metals from either group 1 or 2A, and the anion with the metal is hydroxide. And the metal hydroxide bases will simply dissociate in an aqueous solution to free up their hydroxide anion. So we saw already, we wrote dissolve here. That dissociation to produce the hydroxide, which is very, very good at picking up NH+. It's a very strong base. So let's go ahead and do it for these others real quickly. For potassium hydroxide, the cation would be potassium rather than sodium. And for calcium hydroxide, we get calcium cations. It's group 2, so it's a 2+. And hydroxide anions, and we're going to get 2 hydroxide anions for every 1 formula unit that dissolves. So I'm going to put a 2 there. Okay, so this is just a dissolving process. Weak bases, on the other hand, will not have as high of affinity for an H+. Okay, so have a lower affinity for an H+, and your weak bases will significantly less than 100% ionize to produce hydroxide anions in an aqueous solution. So let's write here, they will less than 100% ionize in an aqueous solution. So let's take ammonia as our example. And I do keep picking ammonia for a reason. And the reason is that ammonia is a really good one to look at if you're going to be moving into biological chemistry, because the bases that you'll be dealing with in your biological chemistry will be amines, and they're very similar in structure to ammonia. But instead of having all hydrogens, they have carbon attached to them as well. So that's why I keep picking ammonia here. All right, so ammonia we already saw will ionize with water to produce ammonium cations and hydroxide anions, but we want to put an arrow back here because there's not just a forward reaction here, there's also going to be the reverse reaction here. And at equilibrium, you're going to have reactant and product present in that solution. So very similar to the weak acids that we just talked about, but of course the weak acids made hydronium ions, not hydroxide anions. So over here I'm going to write that you have NH3 and of course water because it's an aqueous solution, so I'm not going to write that, and ammonium and hydroxide. You're going to have all of these things in that solution. But let's say that your ammonia solution was a 0.1 molar solution. Okay. Because not all of the ammonia is going to ionize, you're going to have a hydroxide ion concentration that is quite a bit less than the 0.1 molar, because not all of that ammonia is going to ionize to turn into ammonium cations and hydroxide anions. Okay. Whereas up here, for these strong bases, if you had a 0.1 molar sodium hydroxide solution, you would have just sodium cations and hydroxide anions, and therefore your hydroxide anion concentration would be 0.1 molar, because for every 0.1 moles of sodium hydroxide that dissolves, you're going to get 0.1 moles of hydroxide. So if you're talking about 1 liter of solution, 0.1 molar solution, then you're going to end up with 0.1 moles per liter of hydroxide in that solution. All right, so let's go ahead and take a look at this reaction and analyze both the forward and reverse reaction and identify the conjugate acid-base pairs. A good review before we go on and talk about neutralization reactions. So in our forward reaction, ammonia is the H+ acceptor. That's why it turns into the ammonium cation. And so ammonia is our Bronsted-Lowry base. Water is the H+ donor. So it is our Bronsted-Lowry acid in the forward reaction. Now let's take a look at our reverse reaction. In the reverse reaction, the ammonium cation is giving an H+ back to hydroxide to form water and ammonia. So our ammonium cation is the H+ donor, or the Bronsted-Lowry acid. Hydroxide is the H+ acceptor. And so hydroxide is the Bronsted-Lowry base in the reverse reaction. So we can see a conjugate acid-base pair here. I'll just write conj, AB, pair. I'll abbreviate it this time. Okay, off by just the presence of one H+. And we can see another conjugate acid-base pair here. And remember that the equilibrium will always favor the side of the reaction which has the weaker acid and the weaker base. Well, hydroxide is an extremely strong base, and so really the reactants are the favored here. So this solution would contain more of the reactants than the products, and again, significantly less than 0.1 molar hydroxide. All right, let's go ahead and erase here, and we're going to talk about neutralization reactions next. We are on slide 4, neutralization reactions. A solution of acid will neutralize a solution of base. We're going to talk about a very specific type of neutralization reaction today. We are just going to look at neutralization reactions occurring between an acid and a metal hydroxide base in an aqueous solution. Okay, so for an acid and a metal hydroxide base, the products of these reactions will always be the same. You will form a salt and water, H2O. The salt will be composed of the cation of the base, which is combined with the anion of the acid. So let's take a look at a real reaction. For our acid, let's use hydrochloric acid. We said this is going to be an aqueous solution. And for our metal hydroxide, let's use sodium hydroxide. Again, aqueous solution. Okay, so our cation from the base is going to be combined now with the anion from the acid. So our salt will be NaCl, sodium chloride, for this reaction. You can check a solubility chart. You'll find that that ionic compound is soluble in water. So I'm going to go ahead and write the state as aqueous. And the acidic proton, the acidic hydrogen, is going to combine and neutralize the hydroxide, combine with, I should say, and neutralize the hydroxide from the base. So you're going to get HOH, or H2O. I'll go ahead and write liquid there for the state. Okay, this reaction happens to already be balanced. So we'll do some more practice with writing these neutralization reactions that occur between an acid and a metal hydroxide base in the problem set number 13. For now, we're going to go ahead and move on to slide number 5 and talk about the pH scale. It is often more convenient to express the acidity of a solution in terms of pH, particularly when you're talking about solutions that have a low hydronium ion concentration, less than 1 molar. And pH is just a measure of hydronium ion concentrations in solution. I'm going to write that here on the board. pH is a measure of hydronium ion concentration, where that hydronium ion concentration is expressed in molarity. So I'm going to write here in molarity. And the pH scale runs from 0 to 14. A pH of 7 is considered neutral. A pH greater than 7 is basic. And a pH less than 7 is acidic. pH is the negative base 10 logarithm of the hydronium ion concentration. I'm going to write that in the equation form. pH equals the negative log of the hydronium ion concentration, which means that the hydronium ion concentration could be found from the antilog taken to the negative pH. So I'm going to write that down here as well. H3O plus concentration equals 10 to the negative pH. Okay. So some very important things to realize about the pH scale. First of all, as the pH of a solution decreases, the acidity of that solution is increasing. I'm going to write that down here. As the pH decreases, I'll just put arrow down, the acidity is increasing. So lower the pH, the more acidic the solution. Now another way to say this, so I'll just write it down here in parentheses, so we're really just saying the same thing over, just saying it a little bit different way, is that as the pH decreases, the hydronium ion concentration is increasing. So as the pH decreases, the hydronium ion concentration of a solution increases. Now, because pH is a negative base 10 logarithm of the hydronium ion concentration, a 1 unit increase in pH will correspond to a 10-fold decrease in hydronium ion concentration. I'm going to write that down here. A 1 unit increase in pH corresponds to a 10-fold decrease in the hydronium ion concentration. So if we have two solutions, let's say one solution has a pH equal to 1, and we're going to compare that to another solution that has a pH 1 unit higher, a pH of 2. So 1 unit increase in pH. Let's take a look at the hydronium ion concentration for those two solutions. So for the pH equal to 1, the hydronium ion concentration is going to be equal to 10 to the negative pH. So 10 to the minus 1. I'm going to write it as 1 times 10 to the minus 1. And remember that the concentration is in molarity. So I'm going to put a capital M. For the solution with a pH of 2, the hydronium ion concentration will be equal to, again, 1 times 10 to the negative pH. So 1 times 10 to the negative 2 molar. So again, a 1 unit increase in pH, a 10-fold decrease in the hydronium ion concentration. So then if you compared a pH 1 solution to a pH 3 solution, that would be a 2 unit increase in the pH. That would correspond to a 10 times 10 or a 100-fold decrease in the hydronium ion concentration. So if you're not quite familiar with the use of logarithms and anti-logarithms on your calculator, then I highly recommend that you tune into problem set number 13, where we will be using these equations to convert between pH and hydronium ion concentration. Until then, let's go ahead and move on from pH and go on to slide 6 and talk about buffers. A buffer solution is a solution that can resist change in pH, even when small amounts of a strong acid or a strong base are added. I'm going to write that up here. Buffers resist change in pH. And buffers work because they have a weak acid and its conjugate base present in the solution. And the weak acid can neutralize any added base, and the conjugate base can neutralize any added acid. I'm going to write that up here. Buffers work because they have a weak acid and its conjugate base in solution. Okay, and so we just said any added acid will be consumed in a neutralization reaction with that conjugate base. So I'm going to write here, added acid neutralized by the conjugate base. I'll just write conj B for conjugate base. And any added base will be neutralized by the weak acid. I'll just write weak A. And in order for a buffer to work properly, the weak acid and its conjugate base need to be present in roughly equal molar quantities. Okay, so the weak acid and conjugate base should be in about the same concentration. So to get an idea of how a buffer solution works in action, let's take a look at a buffer prepared by combining acetic acid, HC2H3O2, which is a weak acid, and the soluble salt sodium acetate. So here's my acetate anion, and it's combined with a sodium cation. Well, we already know that acetic acid, being a weak acid, is going to ionize only partly with water. Okay, that's the definition of a weak acid. Less than 100% ionization in water. So I'm going to go ahead and put my arrow back here. So we can expect some ionization, some release of that acidic hydrogen. Remember, only one of these hydrogens is acidic, so ignore the other three there, to make the acetate anion. And when it transfers that acidic hydrogen to water, water becomes H3O+. So we know that in a beaker, say we're making this buffer solution in this big beaker here, we know that from the acetic acid, we would have lots of covalently bound HC2H3O2, lots of covalently bound acetic acid, and some ionized products. But you might remember we said the equilibrium will actually favor the formation of the reactants here because the H3O+ is a stronger acid than the acetic acid. And remember, it's always going to favor the formation of the weaker acid and base. So we mostly have covalently bound HC2H3O2 and lots of water, because water is our solvent. We don't actually have as much acetate anion. So to bring up the concentration of that acetate anion, we're going to add a soluble salt, which has the anion that is an acetate anion. So when we dissolve sodium acetate into our aqueous solution, we know that it's going to dissolve to free up those sodium cations and acetate anions. And so now floating around in the solution, we can add that we have some sodium cations floating around and then even more of our acetate anion. So we can imagine roughly equal concentrations here of our weak acid and its conjugate base. Okay, so if we add, and I'll go to the blue pen here, if we add any acid to this solution, well, what do all acids have in common? All acids produce hydronium ions in aqueous solution, H3O+. So I'm just going to indicate adding H3O+. pH is a measure of the hydronium ion concentration in a solution. So outside of a buffer solution, we would expect adding any acid, adding more hydronium ions to lower the pH of a solution, make it more acidic. But in the case of a buffer, it does not, because that added acid is consumed by the conjugate base. So I'm going to put the arrow to the acetate anion here. Any added base, what do all bases have in common? The hydroxide anion in an aqueous solution. So I'm just going to be generic and write OH minus. Any added base will be consumed by our weak acid. So I'm going to put an arrow to the acetic acid here. And therefore, again, we won't get a drastic change in the hydronium ion concentration in the solution, and therefore no drastic change in the pH. So let's go ahead and write those reactions out. I'm going to need a little bit more room, so I'm going to go ahead and erase this here. Okay. And I'll go ahead and do it in blue. Okay, so I'm going to write acetic acid reacting with any added base. Doesn't matter if it's sodium hydroxide or lithium hydroxide, so I'm just going to write OH minus. We're going to transfer the acidic hydrogen to the OH minus in this neutralization reaction. We're going to be left with the acetate anion and H2O. As far as added acid goes, it's going to react with the conjugate base, so C2H3O2 with a 1- charge. I'll be generic, I'll just write H3O plus for any acid. Doesn't matter if it came from hydrochloric acid in aqueous solution, nitric acid in aqueous solution. pH is a measure of the hydronium ion concentration, so that's what we're interested in here. That's what's going to change the pH. All right, so in this case, it doesn't change the pH, not drastically at least, because our hydronium ion is going to donate the acidic hydrogen back to an acetate, producing the weak acid, acetic acid. And the hydronium is now H2O. And so we would expect a strong acid to change the pH drastically, because strong acids yield lots of hydronium, and hydronium ions are what change the pH. pH is a measure of the hydronium ion concentration. It doesn't in a buffered solution, because that strong acid is converted into the weak acid, acetic acid. And so the hydronium ion concentration will change very little, and therefore the pH will change very little in a buffered solution. Okay, so in bodily fluids, there are 3 major buffering systems at play. One is the carbonic acid bicarbonate buffer system. Another is the dihydrogen phosphate hydrogen phosphate buffer system. And the last is actually through proteins, which have functional groups that can behave as acids and functional groups that can behave as bases. So that's a little bit different than the kind of buffer solutions we've talked about here. But buffers will be a very important topic in your biological, chemistry, and biology courses. So this will conclude our tutorial number 13. I hope that you will consider tuning in to problem set number 13. Thank you very much.